So in this lab, we will modify our code a little bit to learn about timer interrupts. And we're going to modify the code in such a way that the LED is not just keeping a constant brightness, but we will write a code where the LED is getting brighter and then dimmer, like pulsing. And the way that we can do it is, for example, at the end of each PWM cycle, we can increment the brightness a little bit so that every time an overflow happens, the LED gets brighter and brighter. And when it reaches 100%, then we start to subtract from the brightness. And on every overflow, it just gets dimmer and dimmer until it, switches off completely. So we will learn something about interrupts in this lesson this way, and also about static variables. So it's hard to write a library which enables or disables the dimming. So what we will do is we will just write an example code here for dimming, but we will not change the brightness. So in my main code, I will just comment out these lines. You can select the lines, press Control and /, and it comments or uncomments all the lines that are selected. Basically, this code just says hello world and waits 1 second, hello world and waits 1 second, so that we see that the code is alive. And in these LEDs in it, we will update it in such a way that the LED doesn't just stay in constant brightness, but gets brighter and dimmer, brighter and dimmer, and so on. So how are we going to do that? Usually it's done in the following way, using interrupts. So every time one PWM cycle ends, at the end of the cycle, we change the brightness. As I said, increase it a little bit or decrease a little bit. So to do that, we need to first enable timer interrupts. So what we do is we set the timer 3 interrupt enable using the following command, timer int enable. Then we say which timer, timer 3, and what interrupt. Unfortunately, these flags are not predefined, which is really annoying because otherwise the library is very good. But these flags, they are not an enumeration type, unfortunately, but they are defined with some caps lock name that you can guess. So the name of the flag that we want to enable is overflow flag. So I type timer E and then control space, interrupt enable overflow. So this is the name of the flag. Unfortunately, it's a little bit of a guessing, but it is. So bit fields for timer interrupt enable. The flags that we have are interrupt enable for overflow, interrupt for capture compare, underflow, and so on. But usually people use overflow flag. Some processors don't even have underflow interrupt flag. So we enable this flag. It means that in the timer peripheral, we enable overflow to call an interrupt. And the second level for interrupt enabling system is that we need to enable interrupt in nested vector interrupt controller, NVIC underscore control space and enable ERQ. I think that's the name. And then we give the interrupt name, and then in interrupt enable register, it will enable the particular interrupt. So the name of the interrupt is timer, I think it is NVIC. I don't even remember. I will check out in the previous semester's code because, I don't remember it from my head. So the name of this is timer 2 IRQN. Okay. Sorry, timer 3 IRQN. So this is the line. So with this line, we enable timer 3 interrupts. Whatever interrupts we have enabled inside the timer 3, we enable globally. So you have to remember that there's 2-level interrupt control, which is true for most microcontrollers. So whenever an overflow happens on timer 3, an interrupt will be called. What is an interrupt? Interrupt is a special function which has a special reserved name for timer 3 interrupt. It looks like this, void, and the predefined interrupt name is timer 3 ERQN, I think. Let's see. IRQ handler. So this is the ending of the function. It doesn't accept any values. It doesn't return any values, but it's predefined. I cannot just come up with some interrupt name that I want. These are the reserved interrupt names. And when an interrupt happens, the linker links the interrupt to this function. If this function is undefined, it just returns immediately. But if you have written implementation of this function, then it goes to this function. So our function's name is timer3 IRQ handler. So whenever an interrupt happens, we want to either increase or decrease the value of the brightness. So first of all, what I will do is just, I'll write, I don't know what the brightness is, so I should read what the brightness is. And it can be done in the following way. I will read it into some variable with function timer compare get. So, so brightness level equals to timer compare get. Oh, it's not even available. Okay. Let me check in this thing. Top get, top set, compare set. Okay. Then I can read the value of current brightness by directly reading from timer 3, capture compare, buffer, second channel from 0, 1, 2, dot, capture compare value. I think this is the right thing. Capture compare, channel value register. Okay, like this. So with this line, I read the current value. Then I want to increment it by 1, for example. Brightness level plus plus means add 1 to brightness. And then I want to write it back into the timer, and I can either use LED 0 set brightness to set this a little bit bigger brightness, or to skip one function call, I'll just copy this. Timer compare set, and here brightness level instead of brightness percent. And another thing is when an interrupt is called, you need to clear interrupt flag to say that you have managed the interrupt. If you forget to do it, this interrupt will be repeatedly called forever. So what you want to do is do the following thing. I'll just peek into this thing. So you read flags with timer int get. This will give you all the flags that are set, and then you clear them with timer int clear. Because the timer can have multiple interrupts switched on, and you can look at what flag is set, and only that interrupt you can manage. And if there are multiple interrupts, you know it, and you manage all the interrupt flags. because if another interrupt happens while you're managing one interrupt, you don't want to accidentally clear flags that are not managed. So this is how it's done in ARM microcontrollers. So you have to write unsigned 32-bit integer flags equal to timer int get of timer 3, and then timer int clear timer 3 and flags. So these two lines, because while you're managing the interrupt, if this interrupt happens again, you need to manage and handle it again instead of just accidentally skipping it. So initially you read the flags and you clear the flags, and then you do the interrupt service routine. In our case, we read the value, add 1, and output it. And also, when we reach 100%, we want, for example, to set it to 0 again, so that it goes up and off, up and off. So it dims up slowly, but switches on immediately. So if brightness level greater or equal to 100, then brightness level equals to 0 and greater than 100. So it was 100, we add 1, it becomes greater than 100, and we set it to 0. So it dims up and then switches off. Duh. Let's see. I guess this should work. So the thing compiled, size is 19.4 kilobytes. There was probably no errors. So now I will flash it into the microcontroller and see if it works, or maybe it doesn't work. I don't know. Done. Hex file, flash to device, program, and clear. Well, it looks like it doesn't work, so maybe there's some mistake. So let's find out where it is. So, and now let's just investigate why this code isn't really working. So I call LEDs init. I start the interrupt. The timer, sets the brightness of LED. I don't know, thing doesn't work. I compile it with builder. Then I flash it into the device program. Actually we can change the code a little bit. So stop counter during debug halt. Let's see what it does. Oh, okay. Everything's fine. Don't change anything. Now, the code doesn't work, but it compiled without mistakes. So if the code compiles and you can flash it into the development kit, but it isn't doing what you want, the only thing that you can do is use debugger and just peek into the processor what exactly is the processor doing at that point. So now I will click the debug button, and what it does is it recompiles the code, uploads it into development kit, and pauses the kit. Okay, so now what I'm going to do is I'm going to play the code, pressing resume, and I'm looking at the development kit, but it is not doing anything. So I can show you the development kit. One LED 0 is on, but it's not dimming, nothing's happening. So I can pause the code and check out where in the code it's stuck. So it says timer compare set. Okay, it's somewhere here. Now I will use the step into function, And I'll just walk through the code and see what it exactly does. You can use on your keyboard F5, or you can use this arrow and just click it through. So I was inside, let's see, I'm going into print init, okay? I pause it, and I'm again in int clear function. I step into it, and I'm inside this ERQ handler. So from this, I understand that interrupts are being called. So timer 3 interrupt happens, it is happening. So, and I also see the brightness level 4, and then I step into it again, compare set, that's fine, and I exit the interrupt. And then I, step into, and the code, I need to again pause the code, and the interrupt is being called all the time, but the code isn't really working. So let's try to understand what's happening. And I'm in this print init all the time. So actually, this is a very good example. The interrupts of timer are called so frequently that the rest of the code is basically not given an opportunity to be executed. So let's check out. Timer 3 runs at speed of the same as a microcontroller. So microcontroller runs at 14 megahertz. Timer also runs at 14 megahertz, and its overflow value is 100, which means that the processor can only do 100 instructions between two interrupt calls. But in ARM processors, there is this thing that, first of all, when interrupt is called, it takes between 13 clock cycles and maybe even 72 clock cycles, depending on the context in which the processor is, for an interrupt to be called. And then inside the interrupt, I'm reading some value from a memory, so it's 2 clocks here. I'm writing a value into memory, so 2 more clocks over there. Then I'm reading from memory, but through a pointer, indirect, with offset, and with a second offset. So this probably translates to even more lines in assembly. So maybe this thing takes, I don't know, something like 4 clocks. Then I increment the value, then I compare it. This takes 2 clocks probably, or 3 clocks each. Then I uh, call this compare set function, which writes to a register through pointer with offset and with a second offset. And if the optimizations are switched off, then compiler creates a one instruction per each thing. So dereferencing timer pointer is one instruction, adding offset CC is the second, adding channel offset is third, and adding offset of capture compare value register is another instruction. And then when it is done, it exits, but it looks to me that this interrupt is taking so much time that the processor doesn't have any time left between the calls to do anything and change anything. I don't know why the brightness of the LED is not changing. Is it or is it not? I don't know. But the timer interrupts are being called too frequently, so the code is actually stuck, right? So what we need to do is, what we can do is we can add a prescaler to our timer so that the timer runs more slowly and lets some other code execute, So here, timer prescale, it means that the pulse width modulation frequency will go down. Actually, it almost looks like the brightness of the LED is changing, just very slowly. But the rest of the code isn't very much working. I don't know, you be the judge if it's getting more dim or not. So what we can do is we can slow down the timer so that the interrupts are being called less frequently. there are two ways how we can do it. Either we increase the prescaler from 1 to, I don't know, 5, maybe 8, so it runs 8 times slower and it 8 times more time between two interrupt calls, or we increase the top value so it counts up to, for example, 1000. But in that case, we would need to also divide brightness by 1000 and so on. So what we will do is just we will increase the prescaler. Let's change prescaler to 2 so that it runs 2 times slower. Let's try to build the code and check out if it works or not. So I flash to device and I open Termite, clear. I don't know, will it work or not? Okay, at least the other LED is turned on. And the text is also printed. However, look at this. The text hello world should have been printed every 1 second, but it's being printed much less frequently. Let's see. So it is printed 2, 3, 4, 5, 6, 7, 8. It took 7 to 8 seconds to print the next text. So our processor is still being laggy because the timer 3 interrupts are so frequent. So this is what you need to take into account when you are writing a code. The processor, it runs at 14 million instructions per second, which seems like a very big number, but you can easily overload it with very frequent interrupts. And as you saw, we overburdened the processor to such level that it couldn't even execute the code because it was stuck repeatedly being called for timer 3 interrupt like all the time and didn't really work very well. So what we can do is we can just estimate and slow down the timer 3 to acceptable levels so that the PWM frequency is high enough for it to be nice for the eyes, but slow enough for the processor to not be spending 50% of the time in the function. So what we can do is we can, for example, decide, what? I want this timer to have a period of, for example, I don't know, 10 milliseconds. So what does it mean? It means, I don't know, I'll draw it in Paint. So if a period is 10 milliseconds, so one full pulse width modulation thing takes 10 milliseconds. So here is 0. We set it, for example, I don't know, 30%. So it's 3 milliseconds on and 7 milliseconds off. 7 milliseconds. And the one period takes 10 milliseconds. And then the next one starts. On and off. Here's 20 milliseconds. And so on. And then it turns on and off and so on. So, and these don't have to be precise numbers. Those can be also approximate numbers. Let's say we want to have the timer 3 to work at period 10 milliseconds, which means 100 pulses per second, which means it's 100 hertz PWM frequency. In that case, we just need to tune the prescaler to acceptable value, maybe something higher. So our processor can run up to 114 million instructions per second, but the timer needs 100 clocks until overflow because it has 100 pieces resolution. So this is its underlying frequency. And if we divide down the prescaler by 2, then it's 70 kilohertz. It's too high. We want less. 35, 17.5, 8.7, 4.3, 2.1. So for example, I forgot how many times we divided, but we can get pretty big numbers, or pretty small numbers. So 10 milliseconds. Okay, so let's start over. 14 million divided by 100 pulses per full cycle, and then I start dividing by 2, by 4, 8, 16, 32, 64, 128, 256, 512, 1000. So let's see what the prescaler values could be. The biggest is 1024. So at that prescaler, the frequency will be 136 hertz. It will give us something a little bit smaller than 10 milliseconds, but it will be acceptable for us. So instead of prescaler 2, I set the prescaler to 1024, and now I build it. Now I flash it to a device. And now, as we see, the speed of hello world printing is approximately 1 second. So now, since we set the timer prescaler to much bigger value, slowing the timer 1000 times, it now calls the interrupt much less frequently, and the CPU is free 99% of the time to do everything else in our code, and maybe just small percentage of time being spent on timer 3 interrupt. So as you can see, over blowing our processor with useless stuff is pretty simple. And now, if you look at the development kit, actually the code was working even initially when we started it. The timer overflow interrupt was actually dimming the LED, but it was doing it so fast, it did it, I don't know, maybe 1000 times per second, so that it looked like the LED is just on all the time. But when we slowed down the timer, we start to notice that actually LED is being, dimmed up slowly and then dimmed out quickly. But it dims up slowly, and you can see it, and you can check out it on your development kit. Even I didn't change anything logically in the code. I just simply slowed the timer down. Now, the negative effect of slowing the timer down is that you can take this development kit and you can, for example, wiggle it like this, and you will see that our LED number 0 turns into an interrupted line. So LED 1 is on all the time. So when I move it like this, it looks like an uninterrupted line. But the LED 0, which is quickly blinking, when it moves, it turns into, small dots when you move it. So you take your development kit and move it like this, and you see that the LED draws an interrupted line. And this is the problem with pulse width modulation. If the frequency is low, the persistence of vision kicks in, and you see it like dots, not like a straight dim line. So at moving objects, we want the pulse width modulation frequency to be as high as possible, maybe 500 hertz, maybe even higher. But on static objects, it can be also lower. So this is the code with which timer number 3 calls on itself an interrupt on each overflow and increases the brightness a little bit. And now let's update our code a little bit so that the LED is dimmed up and at the same speed dimmed down. So how can we do that? In timer 3 interrupt handler, we will create a new variable which we will call direction, whether it should be dimmed up or dimmed down. And its type will be static unsigned 8-bit integer. So a static variable means two things which actually derive from one another, but usually when you just study about it, you think as two different separate things. Static 8-bit variable direction. So static means, first of all, that the variable remembers its value between function calls. Because if you think about regular C programming language functions, when you call a function and you create a variable, at the end of the function, this variable is discarded, it's deleted, it doesn't exist anymore. Because oftentimes these variables are very small, they're being used like one time in the function, and usually they're just located in a register. And sometimes the compiler even compiles the code in such a way that you don't even need to use the variable, it's being optimized out. But if you want to create a variable which remembers its value between function calls, you have to write static in front of it. And the implication of it, or the implementation, is such that this variable is also stored in random access memory. Sometimes some counters that we use, I don't know, for example, in main code, this 8-bit counter, probably it is not even located in random access memory. It's possible that it's located in one of the registers, so it doesn't actually take random access memory space. But by writing static, it reserves a space in random access memory, and it stores the value of the variable between function calls. So on entering the function, it reads the value of the variable from random access memory, and at the end of the function, it stores the value of the variable into the random access memory. And so when you call the function next time, the old value is read from it. So static means remember the function, remember the variable value between function calls by storing it in random access memory. And the third implication of this is that all variables that are stored in random access memory, like global variables and static variables, are all automatically initialized to 0 by startup code. As I mentioned, before your main code is called, a startup code is called, which is located in CMSys, EFM32, Leopard Gecko, startup GCC assembly file. In this code, there is a small assembly code which initializes all global and static variables to 0. So I'll write a comment that static variables are initialized to 0 by default. So you create a static variable, you don't have to write a direction equal to 0. It's automatically set to 0. So, and we will write the code in the following way. We have created this direction variable. And when we want to calculate the new brightness level, we will write the code in the following way. If direction is equal to 0, we want it to dim up, brighter. So brightness level is incremented. And if it reaches 100, then so basically I'll cut this part of code, paste it here, and write it in the following way. We read the brightness, then if direction is 0, brightness is incremented. And if brightness reaches more or equal to 100, instead of setting it to 0, we just set direction direction equals to 1. And that's it. And else here, if, well, basically, else if direction is 1, then we want to decrement brightness level. Oops. I'll just copy the name. Brightness level minus minus. Minus minus means decrease by 1 at the end of this line. And if brightness level is less or equal than 0, we want to change the direction equal to 0. Okay, so we enter the function, we read the old direction value. If direction is 0, it means dim up, then brightness level is incremented. And if brightness level reaches 100, then we change the direction. So next time when we call the function, direction will be the opposite. It will, instead of being 0, will be 1, and brightness will be decreased. So we decrease it, 100 times until it reaches 0. And when it reaches 0, direction is changed to 0. And after 100 times, direction is equal to 0. And the brightness will now be incremented until it reaches 100. And then it is changed again, and so on. So the brightness goes up, and then it will go down, up and down. And to make our code better, we should change brightness level to int32 instead of unsigned int32, because we're comparing it to 0. And if we accidentally somehow made the mistake that it goes under 0, unsigned integers, when you subtract from 0, then they become very, very big. They underflow to a big value, and the mistake is imminent. So this will be the correct way to write it. And now let's check out, let's build it. Let's check out if we have problems. Then flash to device. Oops. Program. Let's open the termite and let's check out if it works. Okay, now it dims up and dims down slowly. Of course, if you look at some old Apple MacBooks, they also had this breathing power light, which was dimming up and down, and to show that the computer is sleeping as opposed to being switched entirely off. And of course, that dimming was more beautiful and more sophisticated, and it really felt like breath of a human, because the pulse width modulation algorithm was a bit more advanced. It didn't dim linearly up, but with some normalized smooth shape. This is just very simple brightness up and down. But if you want, you could also write a more advanced interrupt service routine and change the dimming to something more smooth and more beautiful for the eyes. You would do it this way. Okay, so now I will show you all the code that I have, so you can check it and type it into your application. Then you compile it, check out that it works, and then you upload it to Artus so that I can see that you did this lab and I can give you a pass on this lab. Okay, so in LEDs.c, this is the first part of the code. You can pause the video and check that it matches your code. Then a little bit further down, I have line numbering turned on, so you can see, in which line you are, and you can compare the lines if you want. And this is the end of the code. This is LEDs.h. and this is the main code. Calling set brightness from main code in this small example application would be useless because the brightness is automatically dimmed up and down. But you could modify this code in such a way that, for example, if you want a constant brightness, you set it constant and disable the timer interrupts. If you disable them, then they're not called and the brightness stays at your level. And if you want to enable dimming it up and down, then you call some function LED0 dim, and it will start dimming up and down because you just enable the overflow and underflow interrupts. So this code looks like this. If we want to, we can, for example, write our code in this way. Let's just update it because we will need to use this code a little bit later. So leds.h file, we will add the following one function, void LED0 auto pulse void. When you call this auto pulse function, it just starts pulsing up and down, up and down. And when you call set brightness or on or off, instead of auto pulsing is switched off, and the brightness is just constant. So let's copy this auto pulse function and let's write its implementation. So to cancel the auto pulse, we can either disable timer 3 interrupts locally or disable timer 3 interrupt globally. I don't even know. I think it's basically the same thing. Maybe it's a better idea to disable it globally, so that global interrupting is, less loaded. So to turn on LED0 auto pulse, we will simply enable timer 3 interrupts. And in initialization code, I will delete this line so that by default, it's switched off. Actually, I will change it to a little bit different line. I will call LED0 set brightness 0. Or better yet, just, set it off. LED0 set brightness 0. So I want initially the brightness to be 0 or the LED to be switched off. Because if I don't call it, maybe there's some old value in timer 3 CC register and it's not off. Maybe it's some other value. So I call it and I switch it off. Now, when I call LED0 auto pulse, I simply enable timer 3 interrupts, and this interrupt is being automatically called. And when I call set brightness, then not only it sets brightness to some level, but it also disables the interrupts. And I think, I'm just guessing, that the function name to disable timer 3 interrupts is nvic disable ERQ and timer 3 ERQN. And also, yeah, basically that's it. And when I call LED on, it calls LED0 set brightness 100%. And when I go into it, it automatically disables the interrupt of timer 3 and sets the brightness and exits. And when I call LED off, LED0, then the brightness is set to 0, but inside the set brightness, it also disables the interrupts. So this is how it works. And now let's, test the code. So set brightness automatically disables auto pulse and sets the brightness to certain level. LED0 auto pulse automatically starts pulsing. LED on and off automatically switches on or off and disables the pulsing of LED0. So now in the main code, we need to kind of, check that everything works. So let's do it this way. We call printf hello world, And then we want to, for example, first set brightness to 0%, LED 0, set brightness, to 0%. And then we want to delay 1 second. Then we want to, for example, set brightness to 25%, and wait 1 second, set it to 50%, and wait 1 second, set it to 100%, and wait 1 second. Then we want to, for example, switch it off, LED off, LED 0, and then delay 1 second, LED on, LED 0, and wait 1 second. And then we want to enable LED 0 auto pulse on, and 1 second is maybe a bit too short period of time to fully see the dimming, so I'll just put that it pulses for 5 seconds, for example. So the test code will be like this: brightness 0, 25, 50, and 100%, then off, then on, and then auto pulse for 5 seconds, and starts over with brightness 0%. So I build it. I guess there's no mistakes. The code size is still 19 kilobytes. So working with some peripherals actually doesn't really take that much space in the flash. So I flash it to device, program, and clear this screen. And let's see if it works or not. Okay, so I'll put the development kit here. Okay. So it looks like it works like this. It's off, 25%, 50%, 100%, off, on, and then dimming, off, on, on. And it's pulsing. Off, 25%, 50, 100%, off, on, and dims, off, on, off, on. Okay, so it looks like this code works pretty well, so no problems with that. So now I will show the code again. So this is main. You can pause the video, type it down. This is the bottom part of main function, like this. Then leds.h code, you can type it down. Then leds.c, I'll show it from the beginning. So what we did in this lesson basically was slow down the timer 1000 times, setting prescaler to 1024. Then we enabled its overflow interrupt, but to disable the auto pulsing, we didn't turn on the global interrupt for timer 3, just the local interrupt. And we set the brightness to 0. So both local and global interrupts need to be switched on for it to work. This is the timer interrupt function. Just on every time the timer overflows, it either increases the brightness a little bit or decreases. And starting auto pulse means enabling this timer 3 interrupt to be called every time it overflows globally. And when we call set brightness, it's automatically stopped auto pulsing, and the fixed brightness is set. And LED on and off is the same. Okay, so these are the codes. Type them down, try them out, try to understand how it works. Compile, upload, and check out that they work. And when you are done, when you have written all the code, then put it in a zip archive and upload to the Ortus so that I can check that you actually did write the code and follow through this lab. So that's all for today. I hope everything works for you well.